Okay, so we're going to do a max-min problem, a calculus-based problem that you would use in some type of engineering problem. And it involves, as it says in the problem, starting with a sheet of cardboard. So we're going to start with a piece of cardboard that is 10 by 15. 15 by 10. And we're going to make it into a box. And I decided to do the harder one right away, which would be a box with a lid. It's quite a bit easier to do this without a lid, and I thought it would be a waste of our time, so we're going to do it with a lid. So this requires a little bit of spatial visualization skills, but I'm going to start. This whole problem is predicated on doing one simple thing, and that is chopping a little X out of the corner of the box. The only decision I have to make is how big do I want that box to be, because the rest of the problem falls into place based on the value of X. So notice if I cut a X out of that corner, I got to cut an X by X out of that corner. And that starts the process. So for those of you that are having trouble visualizing, hopefully you can see that if I connect this, do you see that this guy is the front flap of the box? So you got the cardboard sitting there flat. If I chop those two things out, you'll have a flap sitting there. I fold that flap up, and I now have the front of the box. Yes? Yeah. Everybody's good? Yep. Excellent. So then we're going to have a side flap, or two side flaps. So if I extend this, we'll have, whoop, nope, wrong one. Back up. Try this. We're going to have something like that, and then something like this, and then something like this. Okay? So that will be the bottom of the box. Oh, I don't want that. Back to white. Okay, there's a flap. And there's my two side flaps. Are we good so far? Okay, so then all that other stuff on the other side is going to become the back flap of the box and the lid of the box. If I extend this here and here, all of this is waste. And there's one other thing there, and that is that. Okay, so now you good? You see the box? This particular problem, I want to maximize the volume. However, you could have the problem written very differently. And by differently, I mean you could say, how big can I make the box to minimize the amount of waste? How big can I make the box? How can I maximize the diagonal of the box? There's a lot of different problems. We're going to start with something simple, which would be the volume. So if I take that box and I cut off the squares on the corners and these flaps on the side and I fold it up into a box, I would get a box that looks something like this. We good so far? How tall is that box? X. Very good. Now the fun part. How wide is the box? In other words, I'd like to know, how long is this red distance? Let me get this green stuff out of there. Okay. How long?
10 minus 2x.
Could you explain that, please? First of all, say it louder so they can hear you.
10 minus 2x.
Why?
Because that full length of that side is 10, and then you have two x's, so like one on the top, one on the bottom. So 10 minus 2x.
We good? Any problems? Good. That's the easier one. Now the harder one. How long is this side?
Minus x minus y.
We don't want to introduce another variable. We can, you're on the right track, but we could do it without using a different variable. Luke's about to have a breakthrough. I'm gonna give him the, no, you just, that's it. You gave up. You wave your finger a little bit and then you're done.
Yeah.
That's it. Okay. The finger waving didn't help?
No.
Okay. All right. What do you got?
7.5 minus x.
You're gonna have to explain that.
Okay. So if you cut the box in half in two parts.
Okay, hold on.
The box, the
Hold on. Does everybody see the significance of that location? On the left side of that pink line, I've got an X, and then this distance that we're trying to find, this blue distance. On the right side of that line, I also have an X, which is right here. That's my X by X box. And then I've got another chunk of that blue distance we're trying to find. Back to you, Tom.
So if you just cut 15 in half, you've got
7.5
on either side of the pink line. And so you just take x away because there's a segment x long and a segment blue line long. And so you know that both of those have to add up to 7.5. So 7.5 minus x.
Is everybody good with that? Another way to think of it, he's 100% right, but I'll just give you another way to think about it. If I take this entire length, which is 15, I've subtracted from it an x here and an x there. So now I've got 15 minus 2x, and then two distances that are the same. So 15 minus 2x divided by 2. These are identical, we don't care. Okay, so either one, we're fine. 7.5, whoa, that's ugly. 7.5 minus x. How are we doing so far? Okay. Now, again, like I said, if we're just making a box without a lid, it would be easy. You cut 4 corners or 4 squares out of each corner, fold it up, you got a box. But we want to make things more interesting. We're maximizing the volume, so I need to know what is the volume of that box. Length times width times height. So in this problem, it would be 10 minus 2x times 7.5 minus x times x. Good. Length times width times height. You should have this burned into your brain, so I'll ask anyways, just for giggles. Michelle, we would like to maximize this function. So forget about this problem. Let's just suppose we have a function, we'll call it p. How do you maximize the function p? No? Christian?
Take the derivative,
Boom.
set it equal to 0,
Boom.
solve for x,
Boom.
and then put on numbers,
Boom.
test points.
Boom. I don't fault you for not knowing the last part. Answer the question being asked. Right, yeah, write your sentence and all that other fun stuff, right? So that's the gist of it. Anytime we want to maximize or minimize a function, it's the same process, like he just outlined. So, take the derivative of that. Go ahead, I'll wait.
Okay, and then derivative. Okay, you're smart guy. You're really good at that.
75?
There are two main ways to take this derivative. The reason I didn't give you any guidance is because I wanted to see what method you're using. Neither one is more easier than the other. One does more work on the front end, the other one does more work on the back end. Calculators. You know that, Russell? Bonnie, question for you. don't know why I'm shouting. How are you doing this?
I'm multiplying it out.
Multiplying the whole beast out.
Yeah.
Perfect. That's method number 1, multiply it out. Who's multiplying the whole thing out? Excellent. Anybody doing it differently? Well, the people that didn't raise their hand. Cindy, what are you doing?
I did the multiplying.
You're multiplying it out. Anybody not multiplying it out? You're all multiplying it. Whoa, that's unusual. It's not unusual to be multiplied. Nobody did product rule? Oh, wow. Cool. All right. You're going to make me multiply this out, aren't you? Well, I'll wait for you to get done, then I'll ask you what you got. Teacher trick. When you don't want to do it, have somebody else do it. Not as dumb as I look, you know. Oh, well, maybe I am. Julia, just to make sure we're all on the same page, did you get done multiplying it out yet?
Yeah.
Could you tell me what it is? Not the derivative, just the function after being multiplied out.
2x to the third minus 25x squared plus 75.
Was that last part plus 75?
Yes.
Can somebody confirm?
Correct.
Excellent. Thank you for saving me the hassle. Interesting. Last period we were split right down the middle. Half of the people did this. The other half took that x and multiplied it in here and then did product rule. So that's what I was talking about. If you're doing this method like you all are, all the hard work is in the front end, doing that triple multiplication. If you do it the other way, the product rule, the derivative is easier, but you got to do a bunch of simplifying on the back end. Okay?
Can add an x after the second thing.
Oh, thank you. Yes? Okay, good. What's v prime? 6x squared minus 50x plus 75. Oh, what quadratic? Most of the maximum problems that I've ever seen on the AP test are on the calculator portion. Therefore, you should not struggle with finding the values of x. You have a calculator, use it. You should have the quadratic formula on your calculator, use it. And tell me what x is. Oh, hold on. Before we do that, I forgot this. Let's go back up to the beginning. What can you tell me about my possible choices for x? Luke, you're waving your fingers around again.
No,
No, you just,
that was the whole hand.
that was the whole hand.
Yeah,
Oh,
no
what
fingers.
does the whole hand wave mean?
Nothing.
Nothing?
Nothing
It's
is
warm in here,
Yeah.
right? Okay, can I go to the bathroom?
No.
I really gotta go to the bathroom?
No, I don't want the whole box.
No, okay, I got it. What are the possible values of x? How small can x be, theoretically? 0, correct. It's got to be a little bit bigger than 0. So x, okay, come on, Reedy. I'm an idiot. X has got to be a little bit bigger than 0, but less than? Are you okay? Huh? Less than 5. Why, Ashton?
Because 10 divided by 2 is 5.
Good. If it's greater than 5, we have a box that defies the laws of physics, the international box laws.
Yeah.
Okay, good. Does everybody see that? Now, why it's got to be less than 5? Okay. Now, the reason I bring that up is because that will save us some hassles in a second. Because we take the time to do that, it will make this easier. What, by the way, is x? You all have the quadratic formula on your calculator, yes? Does anybody not? Raise your hand. Good. What is it? Say again.
1.96.
3 decimal places, AP standard.
1.962.
1 or 2? 2. And?
6.371.
6.371. Beautiful. What's the problem? Cannot be 6. You don't have a possible box. So that goes away and we save ourselves some hassles. Okay. So going back to what Christian told us, we took the derivative, we set it equal, we set it equal to 0. We solve for x, we got 2 answers. One answer doesn't make any sense, gets tossed out. and therefore we do a first derivative. Now, normally it would be a first derivative number line, but I'm going to do a first derivative number segment because I know that I have to be between 0 and 5, and I slap a 1.962 in here somewhere. We kind of know what we're going to get for an answer here, but you got to do the work anyways, because sometimes weird things happen. If I put 1 into that quadratic, I get 6 minus 50 is negative 44, plus 75 is positive. That makes me happy because that's what I expected it to be. I would hope that this would be negative, or I'm in trouble. So I put in 4. I get 16 times 6 is some number, a big number, but not as big as 4 times negative 50, which would be, okay, negative. This times 4 is going to be bigger than the other two. All right. What does that tell me? It is a max. A relative max occurs at x equals 1.962 because v prime changes from positive to negative. Beautiful. Last thing, answer the question. So on that problem, it says, where did I put it? What size should the square be cut to obtain a maximum volume? I want that square to be 1.962 inches by 1.962 inches. Problems, questions, concerns? We're good? Easy peasy? Eddie?
You go around, you got the 7.5 minus x for the slide length again.
Oh, yeah. 2 ways to think of it. Let's do this way first. If this line has to be half of the box, because I have an X and a flap, and these 2 flaps have to be the same length, right? Because the top and the bottom have to match. We got a rectangular box. It's not anything weird. So this is 7.5. This distance is 7.5. And I want to find the blue part. So the blue part is the 7.5 minus the X, which gives us this. Or this whole thing is 15 minus the 2 X's that I have here, because this is also X, and then divided by 2, because those are the same length. Okay? Question?
How do you know it's between 0 and 5? Like, how'd you get the 5?
If I look at the shorter distance, let's suppose I cut a square out of this that's bigger than 5, all of a sudden I'm impeding on the other space.
Oh.
So it technically can't even be 5, because you would just,
Okay.
right.
Got it.
Okay. Good? All right, let's do something less exciting. The second problem says, in fact, to do the second problem, we're going to go here and use a graph because it involves a graph. Open, please. There we go. Okay. It says which points slash points on the graph of y equals 6 minus x squared are closest to the point 0, 1. Okay, so we're starting with a function y equals 6 minus x squared, and we want to find points closest to 0, 1. What can you tell me about the function 6 minus x squared? Parabola, keep going.
Concave down.
Downward, it's concave down. Look at him using the fancy calc terms. What's that?
To the right 6?
Nope.
Or up 6?
Up 6. So I'm just going to draw a rough sketch of what this looks like. 1, 2, 3, 4, 5, 6. Yep. Yep. Something like that. It doesn't have to be perfect. And the problem says, what points on that curve are closest to the point 0, 1? Okay. So we understand the problem. And you can see that it's probably going to be somewhere like over here. So let's just pick a point at random. I like this guy over here. Gives me some working space. Where is that point that I just put on the curve? Ashton.
X, 6 minus x squared.
Well done. X, 6 minus x squared. Because remember, algebra 1, that point would be xy. Algebra 2 or pre-calculus would be x, f of x. Calculus, it's x, 6 minus x squared. And I'm looking for this distance. How do I find that distance? Say again? Distance formula. Beautiful. Distance is equal to the square root of x minus 0, quantity squared, plus 6 minus x squared minus 1, quantity squared. Good? Now, here's something that'll make you happy. You don't know how happy it'll make you, but it will eventually. If I want to maximize a square root function, I don't have to maximize it including the square root. I can just maximize the radicand. Okay, does that make sense? Let's suppose I have 3 values. I have a big value, a medium value, and a small value. If I take the square root of all 3 of those things, they stay in the same order. That's still the biggest, that's still the medium one, that's still the smallest. Does that make sense? Good. So I could go ahead and do this as d and say, okay, write that as the 1/2, then take the derivative by bringing the 1/2 down, reducing it by 1 to get a negative 1/2, then chain on the inside of that thing, and then I get a big, ugly, nasty thing, but I'm not going to do that. I'm going to create a new function, which I'll call p, and I'm going to define p as just the radicand. X squared plus 5 minus x squared quantity squared. I'm not going to worry about the radical right now. Are we good with that concept? Good. That'll save you a lot of hassles. I hope you understand why. Because we don't want to take a derivative of a square root if we don't have to. Now we go through the same process we've talked about already. We're trying to minimize the distance from the point 0, 1 to the point on the curve. So I'm going to take the derivative of this. Actually, you know what? Before I take the derivative, well, you tell me. Do you want to take the derivative of that or you want to multiply it out? Good answer. X squared. You should get, if you're not already, you should be fairly adept at squaring a binomial. Square the first term, multiply the 2 together, double it. Square the last term. Okay, which is x to the 4th minus 9x squared plus 25. Take the derivative, p prime. 4x cubed minus 18x. What's next? Is that equal to 0? 2x times 2x squared minus 9 equals 0. So x is equal to 0. And plus or minus 3 divided by the square root of 2, I believe. All right, bring the 9 to the other side. Divide by 2 would be 9/2. The square root of 9/2 is 3 over the square root. Okay, good. Continuing with this process we've been doing for a while now, we need a p prime number line, or I can just drag that over there. Come on, Reedy. P prime 0, 3 over the square root of 2, and negative 3 over the square root of 2. Arrowheads. Okay, what's the square root of, what's 3 over the square root? You got a calculator. Somebody tell me what 3 over the square root of 2 is, please. I think it's got to be a number that's less than 1, isn't it? Or is it greater than 1? It's 2.12. Okay. So 2.12, that, the reason I want to know that is so I don't accidentally pick a point in a region I don't want to test. So if that's 2 point something or another, I can pick 1 over here. I put 1 in here, I get back in the derivative, remember. 1, that's a positive times a negative, which would be negative. Put in a big honking number like 10. Would be positive times positive. Okay, and then put in negative 1, I would add a negative times a negative, which is positive. And then put in a big negative number would be negative times a positive, which would be negative. Okay, now, because we only did the radicand and not the entire function, things look weird. Like, if you just look at that number line, what does that tell you about 0? It's a relative max. Okay. So if I go back to the picture and line this up properly, does that really make any sense?
No.
Maybe. I mean, this distance we know already would be 5, yes? Stop it, Reedy. It'd be nice if I learned to use my own board. We know that distance is 5. So yes, that's a realistic answer if you consider it a relative max, but is it the max in the whole thing? What happens if I go very far to the right? What's going to happen to the distance then? Keeps getting bigger and bigger and bigger. So the maximum distance, the absolute max would be infinity, but for that small range, we would have that. However, if I come back here, the more realistic answers would be here. 3 over the square root of 2 and negative 3 over the square root of 2, which on the graph would be somewhere like, what did you say that was, 2.1? 2.1 would be like here and here. Okay, so this would be my minimum distance. And what I don't know is the y coordinate. So to do that, I need to come back to here. If I put the 3 over the square root of 2 in there, I get 9 halves, and 6 minus 9 halves is 3 halves. There's one point. Here's the other one over here. Whoops. 3 over the square root of 2, which would also be 3 halves. And there's the answer to my question. There are 2 points. One is 3 over the square root of 2, comma 3 halves, and the other one is negative 3 over the square root of 2, comma 3 halves. We good? Any problems? For the most part, with these max-min problems, the derivatives are usually not that bad. It's getting the formula that you're going to use to take the derivative of that's going to be a little trickier. But once you get that, then you take the derivative and you go through the whole process you've gone through already. Take the derivative, set it equal to 0, solve for critical numbers, put them on a number line. I forgot to include my sentence here. A relative min occurs at x equals plus or minus 3 over the square root of 2 because, what is this? P prime changes from negative to positive. Okay, and then again, make sure you answer the question and make sure you include units if it applies to the problem. So in the box problem, you want to include inches. This doesn't really have units because you're just looking for the 2 points, which we found over here.